Hello, everyone. We're going to talk about bicomodules today for an hour. Comonoids in poly. So if you take comod poly, you get something. And it's a thing that we started calling cat sharp. This is a double category. It's an equipment, if you know that term. What is it? Well, the objects are comonoids in poly. So those are categories. So cat, it has the same objects as categories, but it has two kinds of morphisms. One is called vertical or tight, and these are cofunctors. And another, which is like this, and these are bicomodules. And it's these that we'll talk about today. But you can form things like squares, which is like you have a cofunctor from C to C prime, and you have a cofunctor from D to D prime, and you have some kind of square like this. And we will talk about this, I think, in the case that these are the identities. But we probably won't talk about it in this general case. Although we could. I don't know what we'll do. We'll see, I guess. So feel free to ask questions all along the way. And let's talk about what a bicomodule is. So a bicomodule, this term, as soon as you have a category, as soon as you have a double category like poly is a monoidal category, and you can, every monoidal category is a monoidal category is a kind of bicategory. It's a bicategory with one object, and that's a kind of double category. It's a vertically trivial double category. You don't have to know those words because we're going to get into the actual thing that's poly-ish pretty soon. I'm just saying this for people who do know these words. So if you have a monoidal category, you have a double category, a vertically trivial double category. And whenever you have a double category, you can ask, are my equalizers good there? Are equalizers good? And someone tells you what you mean by that, and you say, okay, let's check some stuff. Do I have equalizers locally, and do they commute with composition and stuff like that? And if they do, well, just that, actually. If they commute with trie, then you get a nice double category of comonoids. So everything I'm about to say just comes directly from, say, I learned it from Schulman framed bicategories. You just copy paste the definitions from there, and you get this category cat sharp, and I just described for you what you get. And so first, I can just write down the definitions, and then our job is to unpack, like, how are we supposed to think about these definitions? So the definition of a comonoid, as we've already seen, is it's like C to C tri C and C to Y, and these have to play nicely together in this kind of way. And stuff like that. But now we want to understand what bicomodules are. And I'm just kind of slowly walking you through that. Remember, C is just an ordinary polynomial. It's just that it's equipped with some more structure. And so in the same way, a bicomodule is just an ordinary polynomial. What is a bicomodule? So a comonoid is just an ordinary polynomial with some extra structure, but we found that that turns it into a category. And so now we want to know what a bicomodule is, and hopefully it turns into something cool. So a bicomodule, well, yeah, what is a bicomodule? Well, first of all, one, it's between two comonoids. You can't say bicomodule. If someone says, I've got a bicomodule for you, the first question is, what are the two comonoids? And so they say, oh, okay, it's C and D. And the bicomodule is P. So let's say P, what is a CD bicomodule? where C and D are categories. Okay, well, a C-D bicomodule is a polynomial P. It's a polynomial P and two maps, just regular old polynomial maps, P to C tri P and P to P tri D. And we'll call these lambda and rho. And this is just copy-pasted from the definition. Okay, so it's this sort of data, lambda and rho. Rho looks like a P, but it's like scriptier. And they have to satisfy conditions just like these had to satisfy conditions. So the conditions they have to satisfy look very similar, actually, to these conditions. Okay, so what do they satisfy? So this would be called, this is a left C comodule, and it's a right D comodule, because D's on the right, and they're like, what is it? And they cohere somehow. And there's a left C comodule structure, a right D comodule structure, and some kind of coherence between them. So let's write out what the does anyone have an idea of what if you're like a category theorist, you learn what you're supposed to do here. We have lambda. We have this data. What should we ask lambda to do? If you duplicate C and copy P, it's the same as, well, let's still do the lambda. And then here, I want to do something else besides duplicate. What should I do? Lambda. Yeah, lambda. So you ask that to commute. You ask this to commute. And this one is rho, and this one is whatever one, P tri delta, and this one is rho tri D. Okay. What else should you do? We use delta.
Got to play nice with the epsilon too.
Got to play nice with the epsilon. P can go to C tri P, but that goes down to P by epsilon tri P. And so I want that to commute. And I want the other one to commute. P tri D P. I want that one to commute. And there's one more, which is the compatibility. So what's the compatibility here? The compatibility is that I could have done P tri D, or I could have done C tri P. Any guesses where to go from both of those? Let's see. Yeah, I think I'll try to draw some pictures next. What did someone say? CPD. There's lambda. Wait, there's lambda. There's rho. There's lambda tri D, and there's C tri rho. Okay, so this is left C. This is right D, and this is compatibility. Okay. But our job is to unfold what all this P nonsense, all this stuff means, right? Actually, I think I said I would draw a picture, so let's see if I can do it. Okay, so we have P, C, and D. Okay, so P splits into C and P. And P splits into P and D. So there's lambda and rho. Why don't you try writing on your paper these 5 equations in terms of these string diagrams? Lambda, rho. Yeah, what do these 3 things say? P, P, D, P, C, P. P, lambda, P, okay.
I drew them as triangle, it comes out easier to see.
Triangles?
Yeah, it slides like P becomes the common wire.
Yeah, P becomes the common wire.
And
Yeah.
then like it's the triangle sliding past each other.
Yeah, triangle slide. Yeah. Anyway, you can draw these, and they're kind of cool, and maybe they're triangles somehow, like this instead. Like that, I guess.
No, like this. Try. It's actually a try.
Oh, actually a try.
Yeah.
That's cool. Okay. Like that, or something? Like this kind of thing? Do you want to draw it, or?
Actually.
Oh, interesting. Okay. Neat. Okay. Yeah, so anyway, you can draw these pictures. I'm not going to do it, actually, because it'll just take too much time. But you can draw these pictures, and they'll always have like the same number of blues and blacks on the right and left. Is that okay? Any questions on those pictures?
Not on those pictures, but
Yeah.
I wanted to ask if Nelson was showing us yesterday how the left comodule has an action of like partitioning a polynomial.
Oh, we're going to get into it. Yeah, yeah.
Okay.
No, yeah, that's our real job. Our real job is to understand what the heck this is. Like this is just definitionally copy paste. Our job is to unpack why. Yeah. Okay, or what this is. Okay. Okay, so what I want to do first is there's various questions. What is a y-y bicomodule? Yeah. What is a y-y bicomodule? Well, it goes from P to y-composed P very quickly. For any set A, AY has a unique comonoid structure. The reason is that, well, you can check it. It corresponds to the discrete category on A elements. So it's just a category with A objects and one identity morphism, which is why it has a 1 on every coefficient. Okay. So when I write this, these are categories. I don't have to say any more to tell you that they're categories. This is the terminal category. Do you have a question?
Oh, just so in the picture of sort of like for the comonoid of like the left and the right sort of acting on P, in that case, like if you acted with just a thing that had only, it was a discrete category, there were no morphisms, you wouldn't be like keeping track of the connections between each time that you acted. So it's just like the, okay.
Acted.
Never mind,
Acted?
yeah.
You're further on?
Yeah, sorry.
Okay, yeah. So we're just trying to piece together what one of these will be right now.
Yeah, sorry.
And so this thing says, I've got this map from P to P. What is a map from P to P? It's like every position in P must go to a position in P, and then every direction must go back. But I know that this maps to Y composed P. I kind of wrote P here. I kind of should have said Y composed P, but that just is P, right? So here this is like an isomorphism there. Anyway, I hope that wasn't confusing. So here, this map must be the identity, or really like the unit or whatever, like the thing that composing with Y is basically identity. So it says that I have this function, this morphism from P to P, but when I just kind of copy it down, this is the identity. Nothing's happening on this epsilon, right? And so this map has to be the identity itself. So there's no data in lambda, and there's similarly no data in rho. No data in either lambda or rho. All equations hold. So what I'm telling you is, what am I telling you? So somebody has a question maybe, but also try to figure out, if I'm saying that there's no data in lambda and there's no data in rho, then what is the data of a YY bicomodule?
Poly. Since the P is P.
Yeah, it's P, yeah. So, right. Great, so YY bicomodules, i.e. cat-sharp, the horizontal maps from Y to Y, is poly. We might get to what a morphism is here. Maybe we should do it. I don't know, I guess. So if you have, I forgot to say two things. One is, if you're going to denote this thing here, one way you could denote this big polynomial, this big bicomodule, is just by like seeing a P there, seeing that it's kind of copied on both sides like that. And so you're kind of, it's kind of like you could kind of just draw it like that. It's just a drawing of this. Okay, that's the first thing to say, yeah.
Is there a directionality implied by this? Like,
This is a left C, right D bicomodule, but there seems to be a feeling of that wayness, and we will get to that.
Okay.
Yeah, it's appropriate. It feels good that it's that wayness in some way, yeah. Okay. Okay, what was I going to say about that? Yeah, so that's how we're drawing them. Sorry, I forgot to say that there. And maybe I should say, what do you think a map between them would be? Like if you had a bicomodule, I'm going to erase this picture. So, or I'm going to put it here. So if you have a bicomodule between C and D, and another bicomodule between C and D, a map between them, any guesses on what it is? It is, P and P prime are not categories. They are polynomials with some extra data.
Yeah, but doesn't have good.
So it should go P to P prime alpha. This goes to C composed P. This went to C composed P prime. This went to P prime composed D. This went to P composed D. Any guesses what you should put here and here? C tri alpha and alpha tri D. And I want these to commute. And that's what a morphism is.
So the alpha and the other thing are cofunctors?
Alpha is not a cofunctor because these are not categories. These are not comonoids.
Oh, okay. Right.
So alpha is a polynomial map. These are ordinary, everyday polynomials, y cubed plus 7y squared. This is a polynomial map, but these commute. Okay. Over here, there was nothing to check. It was saying that, oh, I need a map from P to P prime, and I need it to commute with like if this is alpha, I needed to commute over here with lambda and lambda prime. Y compose lambda alpha, but this commuting is no data again. Like this is just composing with y, and if you go away and think about it, it'll take you a minute or two to realize, okay, yeah, this will always commute if that's just identity and that's identity. So that justifies the rest, that not only on objects are the polynomials here regular old polynomials, but on morphisms here, the morphisms are just polynomial morphisms. So we've justified this now. So sitting inside cat sharp in this very huge thing, whatever it is, if you look at YY, you're safe. You just have poly again. Okay, then our next job is to figure out what is, maybe we should do it on the original board. Yeah. Our next job is, or what I'd like to do next is, what are bicomodules from something to 0? And maybe from 0 to something, I don't know. Okay, what is a bicomodule? Let's say C is a category, and P is a bicomodule, but D is 0. Then what happens? Well, on the left, the C comodule part, we don't really know what those are, and we're not trying to learn what those are right now. We're trying to learn what the right-hand side is forcing. Making the right-hand side 0, what does that do? And so we get a map P to P try 0. But these are the constants of P. Do you remember that? When you plug in 0 for y, you just get the constants. And there's 0 is a category, right? Because it's 0 times y. And so it's a category with no objects. It's the empty category. But there is an epsilon for that because you just send every 0 to, there's nothing to do, right? So it's P try epsilon. And this, we said, had to be equivalent, the same. So we took every position to a position, but that position was a constant. So every position in P went to a constant in P. And then when we went back, we got back to the original position. So how did that happen? So P had only constants. So P is some capital P. It's just a set.
So there only exists bicomodules where the right is 0.
Yeah, right.
For sets.
If the right one is 0, this thing is a constant polynomial. It's capital P. Okay, so now we have capital P to C composed P. And when we go down to P, and we have capital P to C composed P, and when we duplicate, it's this, oops. Lambda, C tri lambda, lambda, delta tri P. Okay. So we could, yeah, I suppose we should try to work out what this is. Yeah, it's, I think we have talked about this. This is a P, this is a C coalgebra. This is a set, and this is a map from P to C tri P, right? I mean, we wrote it in the opposite direction, but it's the same thing. And it satisfies these properties, which are exactly what a coalgebra would do. So this is, and if you know the term Eilenberg-Moore, C coalgebra. Did we talk about what those are? C coalgebra. So we talked about Moore machines as P coalgebras, which are these machines. But did we talk about what they are when C is a category or comonoid?
You mentioned it in passing.
I mentioned it in passing. I technically did this last Friday. Okay. Okay. So maybe I should do it. Do you have a sense, Sophie, if I should do this or not? Okay, let's see if we can talk through it. For every object, for every element of this set P, we are able to get, we have this set P, so this is 0, and we can go to C try P. So this map is like the identity. Okay, so we pick some object in P, and it goes into C. That's the first step. It goes into an object of C. So every I in P, which is P of 1, because P is just a set, right? Okay. For every I in P, we have lambda 1I is in C of 1, an object of C. Okay, so we've got this category C. Some weird picture of a category C. And then we've got this set. And that's P. And every object of P maps to some object of C. Agreed? That's what this is saying. If we have a map from P to C try P, every object of P, every element there, goes to a position of this. And then given a direction, so we send this one here, given any direction, we get a new element of P. Okay, so that means this went down here, somebody down here picks a direction, we're required to go to some new, there's some sort of next thing corresponding to this choice of direction there, this choice of morphism. So that's the first step, is somehow for any position, any element of P, we get an object of our category, and given any map out, we get a new P. But then that has to satisfy some things. First of all, it satisfies that if somebody picked the identity map out, we have to return to where we were. So every object down here has an identity, and it must return back to where it was. And second, if somebody figured out, I got this object, it goes down to an object of C, I take a morphism out, then I take a second morphism out, that's what this would say, I go down here, I take a second morphism out, and I compose them down here, and then I see how that lifts up to there, it must be the same thing as taking the first one, lifting it back, and then taking the second one and lifting that back. So what does all that correspond to? It corresponds to that for every position here, every object or element of P goes to an object of C. For every map out, there is a next element for that map. And so we can start to draw that as a morphism, as though it's a morphism in P. And this will be called a discrete up vibration. Which you might think, oh God, I thought this is going to be easy because it was our first example. Well, it is easy. It's just that there's a term for discrete up vibration, and that's what this most naturally is. But there's a term you know more that this is equivalent to. And so what it's equivalent to is this is equivalent to, or essentially, a functor C to set. So what's going on is that every object in P gets an object in C. So if I have an object in C, I can look at just all the elements that went to it. That's a set. And given a morphism in C, I get a morphism from all the elements that went to the first one to the set of all the elements that went to the second one. And then what is P? P is the set. of elements of, like, let's call that functor p twiddle of p twiddle. So for every functor from a category to set, you can add up all those sets, and you'll get p.
I'm sorry, I don't get it. Say that
Yeah.
again.
Okay, let's say C is this category. You have a thing first?
Yeah, I was going to suggest like having a graph.
A graph? Okay, graph.
showing The elements of it. And
Yeah.
showing the like the discrete operations.
Okay, so let's say we have this category. It's got an object called V, an object called E, a function, a map called source, and a map called target. So this is what polynomial is this? This is y cubed, because this object has 3 maps out, plus y. Okay, what is a cofunctor, sorry, a bicomodule to 0? It would be called a graph, because it's going to be a functor from G to set. So what's going on there is you're going to have this big graph. They're going to have, here's what the category of elements would look like. We're going to turn this into a graph. And so in our minds, we're getting a graph. The graph in our minds is going to be W, X, Y, Z, A, B, C, D, E, F. Okay, that's the graph in our mind. And the P that we're getting will be the category of elements, or the elements of this. So that'll be W, A, X, B, Y, C, D, E, Z, F. So this is P. P has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in it. And this maps down to EV. Where does W go? V. Where does A go? E. Yep. Okay, so I told you that for any map out of E, like source, I'm supposed to be able to find out some other object, some other element of P that it lifted up to. That was, remember when we were talking over here, I said, you send any object here, like A, you send it downstairs, and if somebody picks an arrow out, you're supposed to be able to pick a new element of P. That's what this says. Given any element of P, it's going to go downstairs, and given any map out, we're supposed to get a new element of P. So we picked A, it went to E, you said. Someone says source, what do you go to? W, yeah. This is kind of weird board work, but this is like source, right? It's kind of like this maps to source. Source of A is there, and target of A is there, and you can do all that. And so every edge will be able to call out its source and its target, etc. So we can build this graph by just knowing this data, this bicomodule data. Any questions or help on what would be helpful? Should we have a 10-minute, 5-minute think about it? Okay, let's pause the recording in 5 minutes. Yeah. This, I had a P here before. This is G. We're in a graph. The graph is here, and we're trying to figure this out. One thing you can do is you can take this graph, and you can write it as a database with edges and vertices. Every edge is listed here, A, B, C, D, E, F. The source is listed here, and the target is listed here. And these are the vertices. They're X, Y, Z, W. And every source is one of these, and every target is one of these. So what is G as a set? What set is G? If you look at this or this, G is all the elements in these primary key columns. A, B, C, D, E, F, W, X, Y, Z.
Can I think of it as the union of the rows?
The union of the rows, yeah. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, and those are the 10 elements of G. Okay, so this is another way to represent a functor from C to set. It's a database, and yeah. So any questions about anything on this board, or anything so far?
How is this useful in the database?
How is this useful? It's a way. For databases, it's a way of encoding arbitrary databases with foreign keys as coprecives or as functors. And then various ways of moving data are represented by the Bicomodules. So that's, yeah.
Bicomodules represent data movement.
Yeah, Bicomodules represent data movement or data migration. Yeah. Okay, questions about this? About how the data of lambda is recording not only a set, but also how that set, everything in that set is either an edge or a vertex, and how source and target are actions on that set. Any questions? Other questions that came up while you were working? Sorry, I should have asked that first. I'll erase this, and while I'm doing it, you can think of another question. So what we've said so far is that for any category, the C0 Bicomodules are essentially functors C to set. And the morphisms between them will be morphisms between them. So cat sharp C0 is equivalent to okay. Questions on that? Functors from C to set. Okay. Should we do another one, or?
I don't know.
Like if C is y to the naturals, it's this thing where we're allowed to go over and over and over and over. It's the free category in that. Then what is a functor from C to set? Well, it would be a set where we know how to advance I don't know whether this is helpful. It's a dynamical system, a closed dynamical system.
It's like a database with infinitely many secondary keys.
It's like we have a bunch of nodes. I don't know what to call this thing. N for node, and next. We have a bunch of nodes or states, I guess they should have been called. X, A, B, C, D, E, F. A, B, C, D, E, F, G. And every node gets a next state. So the next of A is B. The next of B is C, etc. Yeah.
And if I think about the carrier of, oh my God, sorry. Okay, so the thing you wrote down as a table is like the set to C bit.
Yeah.
And then if I want to think about it as
Yeah. So this is going to have a capital P. And the capital P, there'll be whatever that is, 7. So this is 7. Over here, we had like, yeah. Yeah. Yeah.
Where does the natural numbers show up in the database?
The natural numbers shows up that you have next and next, next, and next, 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 next. Yeah. Often it's, yeah.
Oh, so when you draw that category, there's infinitely many morphisms there.
Yeah.
There's next, propose next.
Yeah.
Yes, and
Right.
But this 7 really is the polynomial, right? It's, yeah.
I'm still a little bit confused about what that diagram with the n and the next arrow, like on the left next to, what exactly is that?
There's a, yeah.
corresponds to the like E to arrow V.
Yeah, this is the thing I drew there, except I just have like
Oh, that's like a representation of y to the n
as a category.
as a category. Okay, thanks. Yeah.
Yeah,
Yeah, there's infinitely many arrows there.
as a category. The duplication is given a position here. You get a unique position here. There's only one, but then given 2 natural numbers, we add them.
Gotcha. Yeah.
It's like how many? Yeah. Okay. Questions about this?
That category has one object.
This category has one object because there's one position here. Yeah. Yeah. And natural number many morphisms. Okay. Questions? Okay, so we haven't, it's almost 10:30 and we haven't gotten into that far, but maybe we'll do like, I don't know. We can either keep going or stop. I guess we can do a hand poll about that. I think what I want to do next is like what Joachim was talking about. So if C and D are discrete, we get back Gambino-Cock multivariate double category. And I know we're not focusing on the double category today, but multivariate polynomials. So if I write P, then P will be J many polynomials in I many variables. Now, what do I mean that it will be that? I mean, all it is it's a bicomodule. It's a single polynomial, not J many polynomials. And it's just a one polynomial. And it's in one variable. All polynomials are in one variable in this class. So what do I mean that it will be J many polynomials in I many variables? I mean that it's going to be the same data as. So maybe I should write that. Is the same data as. Okay. And now I can remove the quotes because now I know what I mean. Yeah.
Why do I care about J many polynomials and I many variables?
Why do you care about J many? Yeah. Yeah. That's a great question. Why should you care about J many polynomials and I many variables? So we could either figure out why this is this or why you should care. Maybe we should start with why you should care. Yes. Why you should care. Okay.
Is it a different category?
No, we're in the same category as we always were. We're in cat sharp. Remember, what is this? This is P is in poly. P maps to P with J.
But P has one variable.
P has one variable. So how can it be many variables? Well, We opted to not think about that yet, but instead to think about why we would care
Why we would care if we were thinking about
if it was true.
if it was true.
Yeah, which it is. But we don't know why that's true yet. We're just going to pretend that it's true until we can prove that it's true. But it's worth doing that because we will eventually be able to prove that it's true. Okay.
This is every math lecture I've ever been to.
Yeah. Okay. Hands for why is it the same data as this versus, first we'll do why is the same data as this versus why is it interesting? Okay, so who wants to know why is it this? Okay, and who wants to know why is it interesting? Okay, okay. All right, let's do why is it interesting. So let's say we just had I and j were the same, and I'll call them M for modes. M equals modes. So you've got a M mode dynamical system. Sometimes it's happy and sometimes it's sad. And sometimes it's preparing and sometimes it's working and sometimes it's finished or whatever. And we want to be able to control the mode. Yeah, we want to be able to control the mode.
Without summing.
Yeah, what? We want to be able to control the mode. So what we're going to do is write down a map. Remember, we used to think it was a good idea to write down maps like this. We called those Moore machines or generalized Moore machines. So one of these will still be a map sy to the s to p. It's just going to have some commutativity requirements on it. Yeah.
So the first time you introduced me to like sy to the s to p, you also called them mode-dependent dynamical systems.
It's true that when I first introduced people,
Sorry.
you're right. It's true that since P can have lots of different, P can have states with lots of different
Interfaces.
So it's like, that one is like the interface has a mode.
yeah, that one is like the interface has a mode. Here we're going to be able to say that the states have a mode. The actual system has a mode, yeah. It's also because when I was thinking about this, I landed in Poly, and I was like, this pretty much does it, but this does it in a way more controlled way. You can dictate which states are in which mode and how mode updates occur.
Wait, but you have to do that anyway when you give the map, because
Let's just go through it.
You only get the output from the state.
Suppose sy to the s is a comonoid. There's an extra degree of mode dependency. Yeah, thanks, Matteo. A comonad in cat sharp. I'm going to tell you a bunch of things that you don't know because I'm allowed to, because we're in phase 2, we're in that part. What that means is a comonad in a bicategory or double category or whatever is like this bicomodule together with a map to the identity called epsilon, and together with a map from it compose itself, from it to it compose itself, called delta. So a comonad will be one of these between two categories now. And that's a lot of data, and these have to do the usual delta epsilon-y stuff. But it turns out that's the same thing as just an arbitrary category C and a cofunctor to, arbitrary category D and a cofunctor to C. So it's not so bad. It looks like it's all this extra data, a new bicomodule with some stuff and some more stuff, but that just turns into, because we're already in comodules, that just turns into a cofunctor. Just like if you take, for people who know things like monads in prof, a monad in prof is just a category with like the same objects as another category. If you know that story, that might help you. If it doesn't, it might not. Okay, yeah.
And these are arbitrary C's and D's?
Those are comonoids. C is a category.
Yeah.
Yep. This is a bicomodule.
Ah, yeah, okay.
And it maps to C, and it maps to decompose D, and stuff like that.
And C is like MY, and D is like SY.
So,
Oh, sorry.
thank you for getting me back here. Yes. So we have, so sy to the s, if it's a comonad, then it has a cofunctor to my. We have okay. Now what's a cofunctor to a discrete category? It's just the same thing. This is the same as a function s to m. Okay. So where are we now? Every state, by virtue of us saying, suppose sy to the s is a comonad, which is all this sort of data over here, comonads. By virtue of that, we've like figured out, oh, that means there's a cofunctor like this, but cofunctors into discrete things are just object labels. So it's the same thing as a map from S to M, a function. Every state gets a mode. Mode. Do you have a question, Andre?
Yeah, while we're talking about M and Y to begin with, what if we want different sets of directions?
Well, because we want something easy.
Okay.
Okay. So Sophie asked, why would I care about multivariate polynomials? And I'm saying, one reason is because we're going to get mode-dependent dynamical systems with more control on the modes than ever before. Okay. Okay. Yeah. Okay. So the first thing is that by virtue of sy to the s being a comonad, like we used to ask, by virtue of being a comonad, we have every state gets a mode. But now, what is going on with P? Well, we don't know why yet, because we didn't ask ourselves why this is true, but we know that P is actually m many polynomials in m many variables. Yeah.
Can you please clarify, like, what is a mode on a state?
Sorry. S equals states. Okay. So what is a state and a mode? Let's see. What is a state and what is a mode? A mode is like sleeping or awake. State is like the entire state of your body, like which position you're in while you're asleep or which position you're in while you're awake. So let's say that there's 10 to the 10 states and 2 modes.
It's like attribute on the
Yeah, but while the only way to move from one state to another, like what this is going to let us do is control waking up and falling asleep. Like remember, yeah.
It's almost like you're doing it at the type level.
Yeah, we're doing it at the type level. That's right. So here, every state, yeah, so let's write what P is. P is going to be P1 plus, I need a new board. So what we said we were just going to believe is that P is m many polynomials in m many variables.
I still don't see how that.
No one knows why that's true because we decided not to do it. Okay. Now, P is going to be P1 plus Pm. Okay. But what does that mean? If P was like y to the, let's say P was like a y to the b plus a2 y to the b2 plus a3 y to the b3, whatever. Well, each one of these could have been one of the modes.
Yep.
Plus 5y to the 7th, whatever. Okay, so maybe this one is a1 y to the b1, and maybe this one is, maybe m is 3. Maybe it's like that. And all this splitting up-y stuff is happening in the lambda. We haven't worked out why, but all this splitting up-y stuff of p is happening in the lambda. And
I think your sum is wrong.
Five y
Yeah, I
to
don't
the
think that's
seven?
right.
Yeah, I think you're
It should be like 2y to the 7 plus.
2y to the 7 plus 3y to the 7 plus 2y to the 7.
3, what did I do? Oh, sorry.
They're all to the 7. Unless you can partition on directions
Okay,
also.
yeah, thank you. Whew, good catch. Okay,
I don't, how does P correspond to P1, P2?
how does p correspond to p1 plus p2 plus p3? I'm telling you that lambda does that.
No, but
Can you just
can you just show me on the board?
What?
I don't.
If I add these three polynomials up, do you not get that?
You do not, you do.
You do not.
Wait, no,
Seven y.
no, you
No,
don't.
you have 7
Now you have
right
you
now.
have 7y to the 7.
Subtract 2.
Yeah, yeah. That should be.
Now it makes
Yeah, there you go.
Sorry. Okay.
This category, not algebra.
Yeah. Okay. Good. This is lambda is doing this. What rho does is it lets us split these variables up. So
The direction?
the directions. Okay. B11 plus B12 plus B13.
Oh no.
That's terrible, isn't it? This is terrible. Let me try it again. So P is y to the 5th plus y cubed plus y squared. And then this would be P1 plus P2 plus P3. And this could be y1 cubed y2 squared plus
So now he's going to turn some of the y's into y's of different variables.
yeah.
But when you like add them up, just like get rid of the subscripts on the y's.
Right. Like if you
Yeah.
lost the ability to distinguish y1 from y2.
I see. Okay, and that's how you. Oh, so the partitioning on directions give you multiple variables.
Yeah. The row of this thing will split the variables up.
Okay.
I just didn't, I kind of wrote that here, but it's like really
And this
awful.
all of this splitting is happening in just one cofunctor.
No. Bicomodule. One bicomodule, yeah.
And what?
Okay. So we're in P right now.
But it's the same. Isn't it the same data as a cofunctor?
No. A bicomodule with some that's from C to C and has a comonoid structure, that's the same data as a cofunctor.
Okay.
That's not, yeah. Okay, so 3 polynomials in 3 variables. And this is how Gambino-Cock and other people who have thought about polynomial functors in many variables would have probably written it. But this is coming to us from just P. Okay, questions?
Y3 or something. You just didn't ever use Y3.
Why not? What about this one?
Y3.
Oh,
Y3.
shoot. Oh.
Replace that. Yeah.
Okay,
So
thanks.
if each equation only had one separate y, so you had P1 that was only y1, P2 that was only y2,
Oh.
P3 that was only y3, then it would be like if you could take that picture with those bicomodules, the 2 bicomodules, and then split it into 3 separate ones. So it was like 3 polynomial maps that are all just like separated from each other.
I'm just going to erase this, even though it's kind of right. It's kind of wrong also. Okay, your question was what again? Say it again. So you have
Oh,
P.
It may not be illustrative. So
Yeah.
if all 3 of those were independent of one another, so they had nothing, they're separate polynomials.
If I have
separate
3
variables.
polynomials in 3 different sorts of variables.
Yeah. So
Yeah.
then you have 3
Oh, yeah,
y
yeah.
bicomodules
Yeah.
that were all separate, just SYBS to P's.
Yeah. If we had P1, P2, and P3.
Yeah.
Maybe your question is this: if you have C, P, and C prime, P prime, D prime, then you can get C plus C prime, P plus P prime, D plus D prime.
And so that's like
So the question was, yeah.
degenerate case of like that,
Yeah.
where they're all totally
Yeah.
separate.
Yeah.
I don't get anything about this
Um,
question.
Max asked, what if we just had a polynomial in one variable, another polynomial in one variable, and another polynomial in one variable? Could we get 3 polynomials in 3 variables where the first polynomial only used the first variables, the second polynomial only used the second variables, and third one only used the third variables? And the answer is yes. But more generally, the question is, if I had a bicomodule between C and D, and a bicomodule between C prime and D prime, could I get a bicomodule between C plus C prime and D plus D prime? And the answer is yes. And his case was y, 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 y. His case was y, y.
Oh, right, yeah.
Yeah.
But
Because
you
if
want
it's
it
just
to be
y,
free.
y, then
Yeah.
sy to the s to p is just sy to the s to p if you just turn it this way. It's like a
Yeah.
polymorphism.
Yeah.
But
Yeah.
I don't get, what I don't get is
Okay.
how you got 3 variables here. Like where?
We're not allowed to ask the question how we got 3 variables because we decided not to do that. we explicitly decided not to do that. And I think you even raised your hand for it. So we are just assuming that's true. Okay? We're just assuming that's true. We're just assuming this is true because we decided not to. But our job was to understand why we care. So that's what we're on. Okay, why do we care? So we have sy to the s. And we also have that every element of s is either of type 1, type 2, or type 3. Because we had this map from S to M. So S is also S1 plus S2 plus S3. And P is S1, P1 plus P2 plus P3. Okay. Okay. Okay, so we have a map from sy to the s to p, which means that every state gets one of these 5 positions, one of these 4 positions. And that's the output. But states that are in mode 1 have to go to this thing. States that are in mode 2 have to go to either of these 2 positions. And states that are in mode 3 has to go to this position. Okay. So once you're in this position, remember, just from this sort of thing, every state goes to a position. Every direction goes back to a state. So suppose I'm in state S2 and I go to this position, and somebody gives us one of these 3 directions to go. If they give us this direction, what state do we go back to?
3.
Oh, sorry.
A state in S2.
3. Yeah. Scared. Yeah. We go to a state in 3. You saved me. Okay, thank
So
you.
the states-
So each of these directions points us to, it tells us which mode we're required to go to. We don't know what state we're going to go to, but we're going to go to a state in mode 3 or in mode 2.
How did you pick
But
the
this-
subscripts?
I imagined P as this polynomial.
But the
I imagined P as 3 polynomials and 3 variables. And I was like, oh, let's just say it's these.
So you could put any subscript you want.
Yeah, 1 through 3, yeah.
So you need 3 polynomials and 3 variables.
Yeah.
Like they have to be the same number.
Because n
Yeah.
is n.
Because M is 3.
This n is 3.
We're talking about my to my. If we talked about my to ny, it would be different.
Yeah. So we're in 3y, sy to the s, a comonoid, 3y. And this is y to the 5th plus y cubed plus 2y squared. And this alpha, the alpha is the thing that, this is like sy to the s is s1 y to the s plus s2 y to the s plus s3 y to the s. I guess this is kind of confusing. Does anyone feel like they can explain it or have a question?
I don't know why you picked a mode from a variable. Like you split it into 3 you said
Suppose P is these 3 polys added together, or P is these 3 polynomials and 3 variables.
Yeah.
Suppose we just believe that that's what this is.
Yeah.
then what does it map sy to the s to p? What is this alpha? This alpha, if it conforms with all the rules, will send every state, we'll partition the states into 3 pieces,
Yeah.
and every state will go to one of the positions in P in that mode. Like if it's in this mode, it'll go to one of these. If it's in this mode, it'll go to one of these. And if it's in this mode, it'll go to one of these.
Yeah.
And then somebody will pick a direction, just like they always do. It'll come back to a state, but this is now typing that state, or moding that state.
Right. I
So
get
that if it's in this one, it returns to a 2. If it's in this one, it returns to a 3.
Right, but why,
Yeah.
why does the subscript of the variable determine which mode you go to? Because the modes correspond to polynomials.
No, the modes are, there's a set of modes, 3 modes.
Yeah, which
Yeah.
correspond to these 3 polynomials.
They do, but they also correspond, that's how they correspond on the left, on the left, but on the right, they correspond also to 1, 2, and 3.
So okay, but so does this only work if you have the same set on both
Yes,
sides?
this only works if you have the same set on both sides.
Oh,
Yeah.
okay.
This only works if you have the same set. If you had different sets, if you had j on one side and I on the other, you'd have j many polynomials in I many variables.
Right.
And you would never be able to say that sy to the s is a comonoid. Because, I mean, it's a comonoid in Poly, but it wouldn't be a comonoid in cat sharp unless this and this were the same.
Ah, okay.
Yeah, thanks. Okay, other questions? Yeah.
When you split up sy to the s, why do you not have multiple variables for y in the splitting? Why don't you have s1 to the s over 2?
That's great. That's a good idea. So it's sy1 to the s1, y2 to the s2, y3 to the s3,
Where those add up to s.
where those add up to s.
What
S1
does
plus
that
S2.
mean?
Well, that means, yeah, that's a great way to write it. What that means is every element of S1 goes to a position in P1, and then given a direction there, it has to go to a direction of the same type as it was.
Do you intend those s1, s2, s3 to be the
So,
same
like-
as those vertical ones?
Do I intend what?
Why do the s1, is that the same s1 as?
Yeah, that's the same S1, S2.
Can I make them different?
No. Because this is a comonoid. Because that's a comonoid, yeah.
Wait, can you repeat the question, Harrison?
Harrison asked, well, you wrote S1, S2, S3 on this side. You wrote S1, S2, S3 as the powers, the exponents. What forces this S1 to be that S1, this S2 to be that S2, and this S3 to be that S3? And what forces it is I keep saying this is a comonoid and not telling you why I'm saying that. But that's why I'm saying that. It's the thing that forces mode to be just a single function. That all the data of sy to the s is all the data of this thing is contained in this function.
I don't understand why you split P into P1, P2, P3.
We
Couldn't
s-
you just label.
We were allowed to split P1 into P1 plus P2 plus P3 by virtue of the lambda here.
But I don't get what it's doing. It's just like factoring out the P. Like, couldn't you just
The
put
reason
labels
is like,
on P
yeah.
directly?
The reason is you might have like a wake mode, a sleep mode, and
I thought the modes correspond to the
Resting, what?
subscripts on the monomials.
sad.
But
Yeah.
I thought the modes were the subscripts on the monomials.
Well-
They are that too.
Which ones? What?
We have threes. There's threes lots of places.
I don't understand.
There's 3 modes, and that's gonna give you 3 polynomials and 3 variables.
No, the sub.
Sorry.
Can I say something that might appeal to the programming languages?
Every 3 on the board means one of these 3. One of these. I've changed it so that every 3 you see will refer to, if you see, will refer to like one of those.
Well, you P1.
I don't know if that's valuable at all, but I did that.
S2, S3, and then there's the 1, 2, 3 subscripts on the Ys.
Yeah.
David, can I say something that might appeal
Well,
to
yeah, you can say
like
something.
Solomon, for example? So Reed gave me a really good intuition for this if you're used to writing AGDA code or Haskell code, which is you should think of these like indexed inductive types or GADTs as opposed to just regular not indexed inductive types, where the indices are the modes. So if you had vectors which are indexed by their length, then the modes are going to be the length of the vector.
Yeah.
Your type was up to that point.
Yeah.
Nat on both sides. So the idea is you should think there's like, we're partitioning this data type up into nat many copies of this data type, where it's vec0, there's vec1, vec2, vec3, vec4, vec5.
A related
can you
point,
write
you can think of these like
like
mutually
GATs
recursive
underneath
inductive types, where you have two modes, which data type you're in, like type 1 or type 2, and the types are mutually recursive, so you can say I
Okay.
want recursively
Sorry.
use the other type.
Now I want to. Okay, thank you. So I want us to say that Harrison was repeating for the camera or whatever. Harrison was saying that it's nice to think about these for functional programmers as index types, or what is this? Generalized algebraic data types. Yeah. Yeah. So you're basically tracking the index. What I'm calling the mode is what you might call the index. Yeah.
My mood is, I now care, which is awesome, but I also am like, I'll leave that as a problem for future surveys.
Great. Yeah.
And I am feeling antsy to go.
Do other things. I agree with that. So we will now break, and that'll be the end of the talk.
Sounds good.
And
Do you have any other like things you want to be like? If I was giving a 3-hour lecture on Bicomodules, here's the other points I would.
yeah, if I was giving a 3-hour lecture, I would say, well, how do you I would talk about composition, and I would start with composition like this. This takes a D set, and somehow when you compose, you get a C set. So I would talk about how you do composition. I would talk about like how equalizers come up, and I would talk about how it migrates data. Maybe I would talk about how like one of these is the same data as a functor from C to poly instead of C to set. So if one of these is a functor from D to set, one of these is a functor from C to poly. It's kind of like all sorts of weird, cool stuff. But yeah, I think that's probably good. Oh, do you have a question? Yeah.
Yeah. Would you ever talk about bundle maps?
Bundle maps, charts. Oh, if I was going to talk about charts, we would talk about adjoints here.
Okay.
So adjoints of like this. This is the same thing as a polynomial. If I force this lambda to be the identity or something, and if you take adjoints, this polynomial will have an adjoint, and like maps between those adjoints will be charts.
Cool.
I don't love that perspective. It's okay. It's not super easy to do. It's not like as easy to work with as just charts. But some people, like David Desmyers, defined charts, which are just bundle maps. These are very useful things for talking about trajectories and things like that. And you can do that with adjoints here. Another way to do charts is like with spans, vertical Cartesian spans and stuff like that. But yeah. Yeah, charts are also the pre-sheaves and arrow category. Charts are also Dirichlet polynomials, where like instead of y cubed plus y squared, you could do 3 to the y plus 2 to the y, and stuff. But that's a whole nother topic, and we're not talking about that. That's not a bicomodule thing.
The arrow category of set.
Okay, thank you. Great.